Guys, let's talk about refraction. Uh, Again, the basic idea is largely the same. You need to have two things. You need to have an interface here, and you need to have a normal. Now, there's a problem with my picture, and I'll try to correct it before I go. When you put these lines down here, you mean that side is polished, like a mirror. You're looking at yourself, the reflection is only on one side. So that is not really supposed to be there. So I'll draw it with a heavy color to delete it or to ensure it's not conspicuous in the picture. So let me just remove it. So I want you to think of this as a boundary, and this boundary separates two things or two mediums. On one side, you have air on the top, and on the bottom, you have water. See, air is up here, water is down here. For example, if you had a glass of water and okay, okay, it's something else. A glass of water like that, and this is water. So the light traveling will come, travel through the air, then get in to the water. Now, what is refraction really? How then do we define the word refraction? The word refraction simply means the bending of light. If you come across that word, refraction, it is nothing but the bending of light. The bending of light. And to make your definition more complete, you can say the bending of light as it travels from one media to another. The word is medium, not media. Media will be plural. The word here is medium. Now, I want you to notice that if you check the position of the laser source here, this is my laser source over here. Let's maybe make it, let's make it, what color? This color. See, your laser will release a light ray or a ray of light. If it was reflection, you'll expect it to do something like that. But this is not reflection. The light is not bouncing. The light will go through. But due to the differences in the densities of the media, like for example, here, if you think about air, the way its molecules will be arranged because it's a gas, they'll be further apart. The distance between particles will be further apart. But in water, because it's a liquid, the particles will be closer to each other, not closely packed, but not the distance between the particles will be a bit, it will be a bit closer or packed. So you notice that when the ray of light is traveling in air, it won't experience as much resistance as it will experience once it gets in water due to the number of particles per a square area. Now, what happens is due to that change in speed, because if you're thinking of it, you can say this will be a bit lighter, this will be a bit heavier, for lack of a better word. It will be lighter work for the incident ray to move through air compared to how it will move through water due to the availability of the number of particles per, let's say, square area. We can say this is maybe 1 centimeter squared, and maybe this is 1 centimeter squared. Sorry, cubed, because I'm talking about a volume or even an area. Doesn't matter. If I compare the same chunk of a square area in air and in water, you will find that I will be able to find in this same space in water, I'll have more particle. That's why in water we have more resistance. Now, because it is not reflection again, we know that the ray is going to get through. Now, what happens once the ray gets through? The ray we could have expected it will go through like that, something like that. But that's not what really happens. You could have thought that ray will go in such a path. But sadly, that's not what happens. What happens is it avoids this path and does two things. On this case scenario, it will specifically bend towards the normal. You can see at the point of incidence, again, this point here remains a point of incidence. At that point of incidence, this refracted ray will bend towards the normal, will bend towards, will bend towards normal. And there's a rule for this. Don't worry, I'll talk about it in a few. And if you were to reverse this figure, for example, and visualize it from water into um, from water going into the air, because here we are very specific the direction of the ray is that. What happens if I reverse the direction of the ray? And this time I let the ray travel in a different direction. Let me give you a hint of what I'm saying. See, if we go that way, let's say that's our ray. What will have been our expectation? Our expectation would have been we could have gone through without anything. So this is where the line could have been. However, that line is not there. And you can see now it's not bending towards the normal. What is it doing? It's bending away from the normal. Because now I'm considering the movement of this ray to move in such a direction. So you can find there will be some cases whereby you will bend towards the normal or you will bend away from the normal. So let me explain those two case scenarios real quick. So if this was my surface over here and I was coming from air to water, so I want you to remember this air is less dense and water is more dense. And this is in terms of what we call optical density. Optical density. So if we have our normal over there, that's our normal. What happens is that if a ray of light was to travel and move from the air, hit the surface, it will tend to bend towards the normal. It will the outcome of its bending will be towards the normal. So if that's your line, it will bend towards the normal. And that's the direction it's traveling. Considering you will have expected it to go through that direction. So you can see it's bending towards the normal. However, if you reverse this case scenario and you make this water and you make this air and you have your normal again, if you allow same ray to come over here, moving from water to air, because water is more dense, is denser, and this is less dense. Once the ray comes out of the water, it will start moving faster, so it won't bend towards the normal. If this was the path we would have expected it to go through, it's going to bend away from the normal because it is increasing in speed or it's gaining some speed due to less resistance. So once one last time, how can you define refraction? You can say a refraction is the bending of light, is the bending of light as it travels, as it travels from one medium to another with different optical densities. That's that's a good definition. So refraction is the bending of light as it travels from one medium to another with different optical density. English here, I don't know if you can say off, but you know what I mean. The water, for example, and the air will have different optical densities. That's kind of the basics. I've taken a few minutes to ensure, you know, someone really sees everything. So I'll finish by just reminding you, see, the ray that always leaves the lens will always be the incident ray. Now, once it hits the surface, let me make it bigger. Once it moves from here and hits the surface, what will it do? It will get bent, and that is the bending of light. So we will call that incident ray. And then the one that goes through will be called the refracted ray. And of course, the line that's usually here is the normal. I'm using weight because I don't want to write too much on that surface. Alright, I'll stop there for now. The next video, I'm going to explain how to apply Snell's law. Thank you.